Okay, how are we doing? Are we circle?
Yes.
Okay, so the next module, module 4, is exponential growth. Exponential growth. And we want to learn the mathematics behind exponential growth. So here's a question. Here's two graphs. Which of these functions shows exponential growth? Which is displaying exponential growth? What do you think? The purple or the red? The purple, of course, right? Both. Both of these are graphs of exponential growth. And so this kind of is the first myth. Mythbusters. Mythbusters. Myth number 1. If a quantity grows exponentially, that means it increases rapidly or it takes off, right? That's how we, as you know, in our common English, we use this phrase grows exponentially. We mean it. We think that it means it just grows really fast, super fast, right? Or it accelerates up. That's a myth, okay? This is just as valid of exponential growth, the red one, as the purple one, okay? So, which of these are exponential growth? Both, right? Neither. Here's the second myth. If it's a curve, it's exponential growth, okay? That's another myth. You see a curved function and people say, oh, it's exponential growth. Not true, okay? These are both quadratic equations. These are both quadratic. And there's many, many other types of curves, okay? Many curves. Exponential growth is a very specific type of mathematical growth that we want to understand the nuts and bolts of, okay? So it's not just any curve, and it's not super fast growth, okay? So that's what our goal is to really, we get done with this module, or even done with the first couple of sections, is we really understand the mechanics of what exactly is exponential growth, because it's very specific, okay? It's very specific. So let's start with, and you already should have a taste of that from your reading, okay? So hopefully the reading has given us some kind of idea. So I want you to start on page 127. Bless you. Okay, and so, of course, exponential growth is going to have something to do with exponents, right? But I'm going to try to deter you as much as we can away from exponents at the beginning, and we'll see why. Okay, so when you're doing this, or let's read this together. It says that these 3 girls discover a secret that no one else knows. We're on page 127. On day 1, each of them tell 2 other people. And after that, everyone who learns the secret on a given day tells the secret to 2 new people. This pattern continues for 15 days. So down below a little bit, they have the 2 quantities. X is the day number, and Y is the number of people who have learned the secret. So it's the new people who have learned the secret on a particular day, okay? So it's how many new people have learned the secret that day. So you'll notice that there's 3 notations: decimal, product, and exponential. Our focus is going to be on the product notation, okay? And I'm going to keep steering you back to focusing on product notation. Okay, so I want you to do this page. If you want to work together, you can. If you want to start by yourself and then check with someone else, you can do that too. Just take about 3 or 4 minutes and work this page, 127. Okay. What's that? Okay, so here's the table. You check to see if you were correct. All right, so let's talk about what's going on here. So here's the product notation for the 4th day, right here. So my question is, why does that calculate the number of people who learned the secret on the 4th day? So why is this so? Why does 3 times 2 times 2 times 2 times 2 calculate the number of people who learned the secret on the 4th day? Christian, I saw you first.
Sure. So it's because each day, twice the amount of people are learning the secret as the day before.
Okay.
Every day, you would double the amount that was there before or multiply it by 2.
Okay, and so
then so every day you would multiply by 2 to get the next amount that you're obtaining.
And so, good, right. So every day, the number of people that learn the secret is twice as much as the day before. So then why 4 twos?
It's been 4 days.
Yeah, because you want the 4th day, right? So the first day it would be just this, 6, and then the second day would be twice as much as that. So we multiply by another 2, and so then the 4th day we will have multiplied by 2 4 times, right? We will have multiplied by 2 4 times. Okay. So what about? I want product notation for number of people on the 37th day. So what would the product notation be? Alex, it's a product notation, how would I do this?
So you would have 3
Uh-huh.
times 2, 37 times.
Okay, you said 3 times 2, and what's happening 37 times? Be specific.
It's the days, the number of days. So
No, but in the calculation, when you said 37 times, what did you mean?
So you would have 3 times 2 times 2 times 2 times 2, 37 times.
Right, okay, good. So we can shorthand that by doing this dot, dot, dot. That's not multiplication. That's just like and so on, okay? So that's like period, 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 and so on. And then we could just say, look, how many are there? 37 of those, right? Because every day it doubles, and so then after 37 days, we will have multiplied by 2 37 times. 37, say factors of 2, right? Factors of 2. Okay. So then they ask the question. So how would you describe on the next page, B, top of page 128, it says, if you were to describe to your friend how the number of people who learn the secret on a given day is growing, what would you say? So how about a child? I would change it to, if you were to describe to a child how the number of people who learn the secret is growing, how would you describe it to a child? So, Aaron.
Every day when the first 3 told the 2 people on the first day,
Okay.
the day after that, those 2 people, the first people told 2 people themselves, and it continues to follow that trend.
Okay. So then how would you be more specific about actually the number of people that learn the secret? The number of people that learn the secret. Nadine.
Isn't it doubling each day?
Doubling each day. The number of new people learning the secret is doubling each day, right? Okay, so in that table, so let's think about this in terms of input and output, okay? Doubling each day. That's kind of the growth here, right? The growth is doubling each day. So in that table, we want to think of this as a function, then what would the input quantity be? Anna, what would the input quantity be if we wanted to think of this as a function? The input, what would the input be? So we got these 2 quantities, and we want to make a function out of it, right? So the function is, you have input quantity and output quantity. What would be the input quantity into the function? Number of days, day number, x, right? Okay, and then so we got these three other columns. Which of those three columns then is the output of this function? Hamid. He says all of them. Agree? Yeah, because they're all just different representations of this same number y, the new people who have learned the secret. So all of these are the output, right? So we said this is the growth is like doubling, right? So it's always multiplying by 2. So here's my question. Relative to input and output, where is the doubling coming into this? So I'm gonna put a sentence. I'll put it here. The blank is doubled to get the blank. Okay? So, for instance, the input is doubled to get the output, or the output is doubled to get the input, or something else, right? So this is either input or output, and this is either input or output, and you're going to finish the sentence. So what is getting doubled to give you what? What is getting doubled to give you what? Think about it, talk about it. What is getting doubled to give you what in terms of input and output? So okay, so this Jared right here. What do you think? What'd you guys talk about? What is getting doubled to give you what in terms of input and output?
Number of people that already know are being doubled to get the number of people that learn.
Okay? Right, and so in terms of, how could you say that in terms of input and output? Not sure. Okay? Walter?
The number.
So, two choices for the first blank, input or output. And two choices for the second blank, input and output. Okay, he's saying input is doubled to get the output. Let's test it. So here on day 3, third day, what's the input? No, what's the input? 3, right? X equals 3 here. And so if we double the input, what do we get? 6. Is that the output? Doesn't work, right? So that idea of taking the input and doubling to get the output doesn't work. Let's see here. Justin, what do you think? What gets doubled to give you what? What gets doubled to give you what? We said it was doubling, right? I saw Fuda. Next. She said the output is doubled to give you the output. So, okay, so if an output is doubled, then which output are you talking about then? Okay, so here we are at 12, and she's saying if we double that, what do we get? Do we get the next output? Try it again. Here's 24 on the third day. If we double it, do we get the next output? Yes. Okay, this is key. So the output is doubled to get the next output. We're thinking about exponential functions. What's the focus is how the output is growing, and it's in this case it's doubled. Okay? In this case it's doubled. What's the key operation at work? Addition, subtraction, multiplication, division, or exponentiation? What's the key operation at work?
Multiplication.
You said multiplication, you said exponentiation. What's the key operation at work in this doubling process? It's happening. Multiplication. Multiplication, okay? And notice that this multiplying that's happening, it's always multiplying by the same number. It's always multiplying, in this case, it's 2. Doubling means multiplying by 2. You're always multiplying the current output by 2 to get the next output. Okay? So, this multiplier has a name. Okay? The multiplier is called the growth factor. So what is exponential growth all about? It's about multiplication on the output by the growth factor to get the next output. And that growth factor, within a given relationship, that growth factor stays the same. In this case, always times 2. Always times 2. Okay, so let's write the function. So what about on the t day? So after t days, what would the product notation be? How many people will learn the secret on the t day? Brooke, could you do product notation for after t days? 3 times t? What will it be? 2 times t. 3 times 2 times t. Austin, what do you think?
3 times 2 to the t.
Okay, product notation. Product notation. What is it? What's happening? After t days, how many people learn the secret? You want to try again? No. Shola. How do we do the product notation for the teeth day? Teeth. Patrick.
It'd be 3 times 2 times 2, dot, 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 times 2, and then that's t times
What's t times?
the number of 2.
Number of 2's, right? So we're going to multiply by 2, t times. So t factors of 2. Because every day that goes by, we multiply by 2, and so after t days, we will have multiplied by 2 t times. And so then what is the exponential form then? Somebody knew. Brian.
3 times 2 to the t.
3 times 2 to the t. Okay? So what's the point of an exponent? What's the point of an exponent? It's not the focus, right? It's just convenience. What does it signify? What does the exponent tell us? Diana. It's just so it makes our life nicer, right? It's just a convenience. Tim, what's the exponent about?
3 times you will multiply be the number of people in that case, but the 2.
Yep.
Every time you multiply by.
That's right, exactly. It's the number of times we're going to multiply by the growth factor. It's the number of times we multiply by the growth factor. So after t days, we will have multiplied by that growth factor t times. So t2's multiplied together is more easily written as 2 to the t. Okay, so then if we wanted to write our function, output, show it there, here, we'll do it here. So our function then would be f of t, the output, or y, is equal to 3 times 2 to the t. But when you see that 2 to the t, know that that's just a convenient way to write what? T2's multiplied together. That's what you got to see. That's what you got to see. So if we wanted f of 100, what would f of the 100 represent? What would that represent? F of 100. What would, if I wrote f of 100, what would it mean? Nina?
It would mean 3 times 2, 100 times.
Okay. Be more, so 3 times 2, 3 times 2, 100 times? That's what,
No, 2 double 100 times.
okay.
So there would, go factor 2, that would be multiplied by itself 100 times.
Okay. But what would f of 100 mean? What would the represent? That's, okay, that's,
It would mean, sorry. It would mean that on the 100th day, that's how many people know.
okay. Learn. Learn, yeah. F of 100 would be how many people learn it on the 100th day. That's right. And it would be 3 times 100 2's, right? 100 2's multiplied together. Okay? And that's everybody on the planet. Okay. So let's do a new example. So here's another example for you to work on. So certain type of, red is the instructions, blue is your tasks, okay? A certain type of cell splits into 4 cells every hour. Initially there are 7 cells in the sample. And you're going to answer questions 1 through 4. Here's 1, 2, 3, and 4. And model how the number of cells in the sample changes. Okay, so let's, at the beginning of the course we talked about defining variables well. Defining variables well. We don't want to ever skimp out on that. We want to keep practicing that all semester. It's really important. So what might we, let's do number 1 together. How might we define what this x value is that I've got here? So if a certain type of cell splits into 4 cells every hour, how might we, Jaden, x? What's that? Hours. How about that for defining a variable, hours?
Oh, hours that the cell divides.
How about Morgan? You want to try? How could we define what x, the variable x? He wants hours, which is our unit. That's good. That's part of it.
Oh,
Hours since the someone initially.
Yeah, so number of hours since the initial measurement. Yeah, that's great. Let's say, I have something like that. I have hours since the first observation. Hours since the first observation. Okay, what about y? So what would be our y variable? Omar.
The number of splits.
Okay, so it could be the number of splits, or we could do
number of cells.
just number of cells, right? So total, and this is now total, not new cells that hour. This is going to be total number of cells, that number of hours after our first observation, okay? So it's a little different from the secret thing. Secret was the new people who had learned it. This is now the accumulated number of cells, that number of hours. Okay, so I think you can take it from there. So you need to complete the table, but I want you to use product notation. Focus on the product notation so we can really get this. And then you got 3 and 4 over here, okay? So product notation for the table, and then numbers 3 and 4. Okay. Go.
So do 7 cells make 28, or do 7 make 11?
You'll think about that. So each certain type of cell, each
Is it
cell splits into 4 every hour. Each cell splits into 4 every hour. many cells? X is 0. It's a 0 cell. So let's go figure out initially our cell. 7 is 0. And how many would there be after 1 hour? 1 hour later. Each cell splits into 4. That's it. Okay, Joe, help me with this table. So, how many cells at 0 hours? How many? Not 1. What do we start with? 7. Okay, so we've got 7, and so 1 hour later, according to what's happening, how would we calculate, right, product notation, how would we calculate how many cells there are 1 hour later? How many? So what happens? Each of those cells splits into 4. So how would you get how many cells you have? It's not double. Each cell splits into 4. Yeah. Right? So in the first hour, you're going to have 4 times as many as you had prior. Okay? So how many, what number of cells in product notation do we have after 2 hours? So, of your name. I totally blanked. Tell me. I know it. I just don't remember. Yeah. Was it? Audi. Right. Sorry. So how many?
So it'd be just 7 times 4 times 4.
That's right. It's 4 times what we had the previous hour. How about after 3? Muhammad. So how many cells after 3 hours? That's it. So we take that number and multiply it by 4 again. Okay, after 20 hours. Corey, did you get how many after 20 hours?
Yeah, it's gonna be 7 times 4 times 4.
Okay.
With 3 dots
Yep.
times 4, and we have the bracket under it. Represent that they're gonna have 24.
24s, right, good. So we got that, and we know that there's going to be 24s multiplied together. Okay, so explain specifically how the sample grows. What's the key operation at work? Who wants to take this? Somebody new. How about Christina? Can you tell me specifically how the sample is growing? What's the key operation at work? So for So is the key operation at work exponent? Not quite. Exponent is just a convenience. How about Jonathan? Specifically, how is the sample growing?
So we got 7 cells each, and usually it's 5 4.
What's that? So what's the mathematics characterizing how this sample is getting larger? That's what I'm asking. What's happening to make that? What's that? By 4. And so what do we call the 4? 4 is the growth factor. It's this number that stays the same, and it's the number that we multiply what by to get what? We multiply by the current output to get the next output, right? You multiply by 4. It's the growth factor equals 4, and that's our multiplier. It's the multiplier. on output to get the next output. Okay, how about the function? So let's call the function g. We call the function g. Who can finish the function for me? Brooke, can you finish that function for me? G of x. Okay, and when we see 4 raised to the x, what does it mean, Austin? When we see 4 raised to the x, what are you actually thinking?
It means that we're multiplying 4 by however many, or we're taking 4 to however many days we're at, or hours we're at.
I liked how you started at first better. So you're taking 4 and doing what? What is that? What is happening there?
By how many hours by 4. We're multiplying by 4 for how many hours since we started.
Yeah, it's not multiplying 4 by the number of hours, right? It's, what is it instead?
Like 4 times 4 times 4,
Right.
whatever,
And how many? Yeah, how many 4s?
x 4.
X 4s, right? X 4s multiplied together. Because if we're on hour 20, what did I say? Hour 20, if we were on hour, say 37, then for 37 hours, for every hour, it got multiplied by 4. So how many times did it get multiplied by 4? 37 times, and that would be g of 37. Okay? 7 times 4 to the 37. You imagine 37 4s multiplied together. Okay, so let's summarize. So at the beginning of class, we said exponential growth is not just skyrocketing growth, and it's not just a curve, right? It's something specific. So here's the summary. What is it? It's repeated multiplication by the same value over and over again. That's the nuts and bolts. Repeated multiplication by the same value over and over again. And what is that value called? That we keep multiplying by? That's our growth factor, okay? And that growth factor, it multiplies on what to give what? Output to give the next output. So this is, see how specific that is? That's incredibly specific. If it doesn't follow this, it's not exponential growth. Okay? If it doesn't follow this, repeated multiplication by the same value over and over again, it's not exponential growth. The exponent part is just convenience to represent this repeated multiplication. That's all the exponent is. The real focus is multiplication. Okay, so why don't you go to page 131. So, a couple changes. The first change is, this is school enrollments, okay? So that, the school enrollments is changing in a different way for the South High School and the North High School. So the first change is that I want the enrollments to increase, not decrease, both of them. So school number 1, South High School, change it to is expected to increase 3% per year. Okay. School number 2, North High School, the enrollment's going to increase 20 students per year. Okay, so change that first. The next thing is, just for time's sake, all you need to do is work down to like 4 or 5 years. You don't have to finish the tables all the way down. Just work both tables down about 4 or 5 years. Even just 4 is great. Do 4 for both, that's great. So take about 5 minutes to do that.
Except for 0 value, that they get.
Right, the prediction is right. 0 will be the current enrollment. North should be pretty quick. North High School, if you understand what's going on, boom, just rattle them off. South will take a little longer. So like one more minute and we'll talk. Okay, how does North's enrollment grow? How does North's enrollment grow? Malin, did you get to? What's that? It increases. And so, can you tell me what that would be like in terms of values? Yeah, right. So this would be 1780 then. 1800. Good, okay. And so what about the change in North's enrollment? What would the change in North's enrollment be? I got up here and I said, change the problem to increasing both enrollments. And I said it a couple times. I should have looked more carefully when I walked around. All right, so how is the enrollment changing? So what's the change in N? 20, right? And then what about the next year? You always go up 20, right? And how is the years increasing? By one each time. So look what we have. Well, let's come back to this. All right, so what about this? Here's where it gets a little trickier. How did you calculate if it started in 1980 and increased how much? Increased 3%. So how did you do the calculation of 3%? Alex?
I multiply whatever value S was by 1.03.
Okay, so that's a little bit of a jump. That's right, but it's a little bit of a jump. So did anyone do it differently than that? Like a two-step process?
I did
Oh, you did that. That's okay. That's what I'm saying first.
have, say, 1,980,
Okay.
and then you would add 1,980 multiplied by 0.03.
So what's that second represent? So 1980 multiplied by 0.03. Is that awful to read on the screen? Oh, let's do that. Okay. So that's 1980. So what does that represent there? 1980 times 0.03. 3% of that. To get the new enrollment, then we got to add it to the old enrollment, right? Okay. And what'd you get when you did that?
2,030.
Was that 59 increase?
Yeah, 59. But it was like 59.
Yeah, but high school students. Right. To 2039, sorry. 2039, is that right?
Yeah.
Great, thank you. Okay, so then the next year it goes up 59 again, right?
I got 61.
No, why doesn't it go up 59?
They have different numbers.
3% of a higher number is going to be a higher change, right? Does it go up 61 this time?
61 points. Oh, heck.
So it will be right at, looks like 2100. Okay, let's do it one more time. So over here, we can start with 2100, our old enrollment, and add what? 3% of it, which is 2100 times 0.03. And how much increase is that second part? 63. And so we get 2163. Okay, so looking over here. So then, right here, 1980 plus 1980 times 0.03, what we can do to that expression right there is we could factor out 1980. And when we factor out 1980, what are we left with? 1 plus 0.03. Or 1980. 1980 times 1.03. So for that to get the number in enrollment 1 year later, we could have multiplied by 1.03. Let's do it for this one. So I'm going to factor out 2100. 2100. Factor out, what do we get? 1 plus 0.3. It's the same thing, which equals 2100 times 1.03. So how do we get the next year? This is a big point. Don't stay with me just a minute. What's happening to this? How is this growing? How is the enrollment growing at South High School? 3% increase. But how is it that we can get this next number every time? Increase of 3%. Isn't that the same as? Do you see that that's the same as multiplying by 1.03? I don't have room to do that. So the amount of change is different, but this multiplier stays the same. Well, that should sound familiar. We're always multiplying by 1.03. So multiply by 1.03. Multiply by 1.03 to get the next what? Output. So what is 1.03? Okay, this is exponential growth. So a constant percent increase means you can always multiply by the same value. That's our growth factor to get the next output. So this is exponential growth. What kind of growth is this over here? Exponential growth, right? Shola, what is it? Look at this. Consistent changes in input, or equal changes in input, result in consistent changes in output. What is this? Constant rate of change, okay? So, exponential growth is, hold on a sec, I'm still talking. So exponential growth is multiplicative growth. It's based on multiplication, right? Constant rate of change, now this is kind of a new, look at this, constant rate of change, based on what? Addition, additive growth, Okay, so I figured out a way on the web work that it'll always be due at 1:15. From here on out, web work will always be due 15 minutes before class for you guys. Okay, good, good. All right. No, every day, every time. Tuesdays and Thursdays, always due 1:15.
Yeah.